This is for Math 1710, Section 2.3, dealing with functions. Before we can define a function, we need to first talk about what we mean by a relation, which is basically a set of ordered pairs. Normally we think of x and y in parentheses, where x is the dependent, or rather the independent variable, and y is the dependent variable because the value of y depends on the value of x. There's an example here where we have the ordered pairs 1 and 2, -2 and 4, and 1 and -5, each of them in parentheses, and then the set of the ordered pairs is in brackets, indicating that it's a relation. A function is also a relation, but it has a special feature, which is that for each distinct value of the first component, which is the x in the ordered pairs, there's exactly one value of the second component, which is the y. So we have here the function to be determined whether it's a function or not is the ordered pairs 1 and 2, -2 and 4, and 3 and 4. Each of the x values has only one value for y, so therefore f is a function. As we look at g, we have 1 and 1, 1 and 2, 1 and 3, and 2 and 3. If you'll notice, the 1 for the x value in the first order pair has a value of 1 for y. In the second one, the same x value, 1, has a value of 2. And in the third set of ordered pairs, the value of 1 has a value of 3 for y. So each time, x has a different y value, so that would disqualify that set of ordered pairs as a function. So therefore, it's not a function. As we look at set H, we have -1 and 4, -2 and 1, and -2 and 0. If you'll notice that -2, one time it has a value of 1 for y, and another time it has a 0 for y, so therefore it's not a function either. Now we can do something called a mapping test, and we use ovals to do this, where here are the x's and here are the y's. So for set F, which is the one we're looking at here, we'll write all the x values from set F in the first oval, which would be 1, a -2, and a 3. We'll write all the y values in the second oval, which are 2, 4, and then there's another 4, which we don't have to write a second time. So we're now going to take the 1 in the first order pair, and it says it's connected to the 2, so we'll draw an arrow to it. The second one, it's connected to a 4, and then the third one, it's also connected to a 4. But if you'll notice, there's only one arrow from each x to some y. As long as there's only one arrow from each x, you have a function. So f is a function. We're going to do another mapping test for set H, where here are the x's, here are the y's. It's for set H. So for set H, we have a -4, a -2, are the only two values for x. Then we have a 1, another 1, which we don't have to write, and a 0. So from -4, we go to a 1. From -2, we go to a 1. And from -2, we go to a 0. But you'll notice from the -2, we have 2 arrows. So that disqualifies it as a function. So this is not a function. All right. Now, the set of all x's, this is called the domain. the set of all x's. The set of all y's is called the range. And the x's, again, are the independent variable. The y's are the dependent variable. And we're going to look at some different ways of finding the domain and the range of a particular function. The first situation is where we're finding the domain and the range if we have a set of ordered pairs. So we have already done that up here when we did the mapping test. So we'll go to number 2, which is where you have a graph. So for number 2, part A, you have a graph with certain ordered pairs located on there. So I would suggest that you first identify the ordered pairs. I'm going to do the first quadrant. That's a 1 and 2, 3, 4. Let's call that a 1 and a 6. In the second quadrant, we have a -2 and a 3. In the third quadrant, we have a -1 and a -2. And in the fourth quadrant, we have a 3 and a -4. So we can now do the domain by just listing the x values, a 1, a -2, a -1, and a 3. And we'll put them in the brackets because that tells you it's a set. The range would be the 6, the 3, the -2, and the -4. So that's how we identify the domain in a range when we have a graph given to us. On part B, we have a different situation where we have an oval-looking graph. And I'm trying to copy it off your notes here. So we have this graph. It would be virtually impossible to list all the points that are on this graph. Like on part A, we could identify 4, but there's infinitely many here on this graph. So for the domain, we have a different way that we can do this. It will be all the x values as far to the left as possible, and all the x values as far to the right as possible. And I'll put them in parentheses, but I'm going to show you also that we can use square brackets in addition to parentheses. But on the range, we want to see how far down does the graph go and how far up does it go. So for the domain, the farthest to the left is a -2. The farthest to the right is a +2. If the -2 and the +2 are included on the graph, which they are, right there and right there, we use square brackets. If they're not included on the graph, we use parentheses instead. On the range, the farthest down that it goes is -3. The farthest up that it goes is +2. And again, those 2 points are on the graph, so we use square brackets. This is called interval notation. It's one of the ways that we can list the range and the domain. Also, we have, for number C, we have this graph right here. And we can see that on the domain, the furthest to the left that it goes, as indicated by this arrow, it continues to go further and further to -infinity. And to the right, it goes further and further toward +infinity. You cannot include infinity on a graph, so we use parentheses. For the range, the farthest down that it goes is -infinity. and the farthest up that it goes is positive infinity. So the range and the domain are the same on a straight line graph that has either a positive or negative slope. On your notes, you'll see something called agreement on domain, and that simply says that unless specified otherwise, the domain of a relation is assumed to be all real numbers that result in a real number for the dependent variable. So in other words, any x that gives you a y value, that's a real number. There are two special exclusions to this. One is division by zero, because we know that division by zero is not possible. And also it excludes even roots of negative numbers, such as the square root of -6. That's going to be imaginary, so therefore we do not include it in the domain, because the normal coordinate system is for real numbers only. So division by zero, an even root of a negative number, those are excluded from the domain. We have also another way to determine if a graph is a function, and that's by the vertical line test. And it says that if you take a graph, and I'll draw A out here for us. If this is our graph, if you can draw a vertical line anywhere on the coordinate system for this graph that touches the graph more than one time, such as like right here, touches there and touches there, then this is not a function. Even if you can draw the dotted line out here, a vertical line, or here, or even here, these two that doesn't touch the graph at all, here it touches once, but you have to be able to draw the vertical line anywhere. You can't just pick and choose. So for part B, we have this graph. It doesn't matter where you draw a vertical line, it's only going to touch the graph one time. So this first one is not a function. The second one is a function, because the vertical lines do not touch the graph more than once. And for part C, we have this graph, and you can see that right here, it touches more than once, so it's not a function. So the vertical line test is very useful whenever you have the picture of a graph given to you. We also want to look at identifying whether something is a function, and then also giving the domain and the range. And the first one, under number 5, y equals x plus 4. I would recommend that the best way to do this is to use your graphing calculator. So I'm going to go to y equals, and then clear off what was on there, and I got x plus 4, and then hit the graph button, and you'll notice that the graph is a vertical line, or not a vertical line, but a slanted line going like this. So that's obviously going to be a function, because you can draw a vertical line anywhere and not touch the graph more than one time. So let's go to, we need to do the domain and the range on these, on this one right here. The domain is from negative to positive infinity, and so is the range. That will always be true of a linear function, which makes a straight line. All right, the second one is y equals the square root of 2x minus 1. If we put that on the calculator, go back to y equals second square root 2x minus 1, close your parentheses, and graph it, you will get this graph. It'll look like this. And that is obviously a function, but we still have to determine the domain and the range. The way that we do that is we take this and set it equal to 0 and solve for x. So that's 2x equals 1 and x equals 1/2. That tells us this point right here, that x is 1/2. So the farthest to the left that this graph goes is 1/2 for x, and it goes continuously to the right to positive infinity. Infinity always has a parenthesis. Since 1/2 is included on the graph, because it's equal to 1/2, we make that a square brackets. So that's the domain. The range obviously starts at 0 right here, and it goes up to positive infinity. So 0 is on the graph, so we'll make it square brackets and parentheses for the infinity. For part C, we have y squared equals x. Solving for y, we get y equals plus or minus the square root of x. When we put this on the calculator, we do it in two parts. Let's clear this off. Y equals plus the square root of x, so that's second square root x, close your parentheses, and then come down to y2 and do negative second square root of x and close the parentheses, and then hit the graph button and you'll get this shape. Well, what happened here? I didn't get the second one in. No, I forgot to go down. Okay, well, I didn't clear that. Let's go back and clear that. So we got second square root of x, close your parentheses, go down to y2, negative second square root of x, close your parentheses. Now the graph button. So what we end up with, and I'm not getting it, yeah, there it is. Okay, so it looks like this. And that obviously fails to pass the vertical line test because it crosses here and here. So this is not a function. Not a function. But we can still do the domain. The farthest to the left is 0. It goes to positive infinity. 0 is included, so we use square brackets, parentheses for infinity. The range, the farthest down that it goes is to negative infinity, and the furthest up that it goes is to positive infinity. So we use parentheses for both of those. So that's how you do part C. And then part D is y equals 5 over x minus 1. To do this one, let's clear this off here. I'm going to put 5 divided by, and I'm going to put the x minus 1 in parentheses, x minus 1, close your parentheses, and then graph it. When we do that, we get the graph comes out in two parts. Right here and right here. And there's a line, if you'll notice, coming down through here like this. On my graphing calculator, it's a solid line, but technically it's dotted. Some calculators will give it to you as a dotted line. So the graph is in two parts. the idea is that if you set this equal to 1, or 0 rather, you get x equals 1. So x equals 1 right here, that's called a vertical asymptote. And what we mean by a vertical asymptote is that the graph gets very near to that dotted line, the vertical asymptote, but it never actually touches it. And that's because at x equals 1, the denominator is equal to 0, and that excludes x equals 1 from the domain. So the domain is going to be in two parts. It's going to be this part over here and the part to the right. So on the left, the furthest that goes to the left is negative infinity. The furthest that goes to the right is this 1 right here, but 1's not included, so we have parentheses for both of them. Then the other part, it starts at 1 and goes to positive infinity. And again, the 1's not on the graph, so it's in two parts, and we put a U between them to indicate the union of these two parts. The range can be done by noticing that the farthest down that it goes here is negative infinity. The furthest up that it goes on the left side here is to 0. And neither one of them is included. Then for this part, the furthest down that it goes is to 0, and the furthest up that it goes is to infinity. And we again use a U for union. So this is one that has two parts, and we have to be aware of the fact that it has the two parts. Now, the next thing we want to look at is called function notation, which says that if y is a function, then we can write it in a special way. Since y equals 3x minus 4 is a function because it graphs into a straight line, we can say that we have f of x is equal to 3x minus 4. So these are interchangeable. It's just a matter that when we know something is a function, we use this, which we read as f of x. F is a function of x. It's not f times x. So we can use this under part H to evaluate functions. If f of x is negative x squared plus 5x minus 3, and g of x is 2x plus 3, we can find certain values. For example, f of x here is f of 2. So that means that we put a 2 into the f function up here every time we have an x. So that's negative 2 squared plus 5 times 2 minus 3. You can put this on your calculator or you can work it out manually. So that's negative 4 plus 10 minus 3. So that turns out to be 3. So f of 2 is equal to 3. We'll come over here and do f of q. And that simply means you put a q every place you have an x. So that's going to be negative q squared plus 5q minus 3. So that's what f of q equals. And the last one, g of a plus 1, means you put an a plus 1 into the g function every time you have an x. So 2 times a plus 1 plus 3. We do need to simplify this, so that's 2a plus 2 plus 3, which gives you 2a plus 5. So g of a plus 1 is 2a plus 5. Now here we have another example, example 2, where you have a set of ordered pairs, negative 3 and 5, 0 and 3, 3 and 1, and 6 and negative 1. This is a set of ordered pairs. we need to find f of 3. So we go to where x is equal to 3, which is this right here, and we see that f of 3 is equal to 1. So f of 3 is equal to 1, which means that 1 is the y value. We have one more example here, example 3. X minus 4y is equal to 5. We're going to rewrite this by solving for y. We'll subtract x from both sides, and we'll get negative 4y equals negative x plus 5. Then we'll divide by negative 4 on each term, and we'll get y equals, this would be a positive 1/4 x, and this would be negative 5 over 4. So we can now take the y and write it as f of x, because this is a linear function, and if it's a function, we can use f of x. 1/4 x minus 5 over 4. Then we're going to find f of negative 2, which means we put a negative 2 in for this x. So that's going to be 1/4 times negative 2 minus 5/4. So that's negative 2/4 minus 5/4, which makes negative 7/4. So that's what f of negative 2 equals. And we can also do f of a, which means we put an a in for the x, so that's 1/4 a minus 5/4 instead of 1/4 x. All right, at the bottom of page 15 in your notes, you will see that we talk about different types of functions. The first one being increasing function, where as x increases, so does y, which means y goes uphill. Decreasing means as x increases, y goes downhill. And constant means that y stays the same. So we have here at the bottom of the page some examples. This first example, A, as x increases to the right, y goes up, so that's an increasing function. On part B, we have this graph. As x increases, y goes down, so this is a decreasing function. And on the last one, as x increases, y stays the same, so this is constant function. So either it's increasing, decreasing, or constant. Now we have one final example, which is a combination of these three. So we have 1, 2, 3, 4 this way. We go 1, 2 this way. And 2 more to go down like here. Over here we go 1, 2, 3, 1, 2, 3, 4. And we go over here 2 spaces and down here. So from this point to this point, it's increasing. From this point to this point, it's constant. And from this point to this point, it's decreasing. But we want to identify the intervals now. This is -4, and it increases to -2 for x. And both of those are on the graph, so we'll use square brackets. It's constant from -2 to +2. Square brackets on those. and it decreases from 2 to 4. Square brackets again. So on this particular graph, it does all three. It increases, it decreases, and it's also constant. So that concludes this section. Do not do the assignment in your notes. Do the assignment on Pearson. Thank you.